Quick recap of the math we were looking at last time. If you have an exponential function, presumably we've got an exponential e to the something. And since we're talking about decay, we're going to assume that it's e to the negative something, which we usually write as e to the negative lambda t, where lambda is just some constant that generally relates to the rate at which something is changing. Also, if you have a constant multiplier outside the exponential function, it's still an exponential function. Let's say we write this as capital C. Because what would that do? If you're just graphing some function and you get some graph, but then you multiply it by a constant. Like let's say you take this function and multiply it by 3. How would that modify the graph itself? What would that times 3 do to the graph?
It would just make it wider?
Not wider. It would make it wider or narrower if you had a multiplier inside the function, affecting t directly. But a multiplier outside the function is more directly affecting y. So that's going to do what instead?
Amplify it in this case?
Yeah, it's going to amplify it. It's going to stretch it in the y direction. In general, a multiplier on t inside the function causes it to stretch or compress in the t direction. A multiplier outside the function more directly affects y, so that's going to stretch or compress it in the y direction. In particular, a times 3 is going to make this graph the same basic shape. In fact, it's going to have all the same zeros, but it's going to be 3 times steeper. All the y values are going to be 3 times as big. But it's still the same basic shape, and we'd say it's still the same type of graph. So a multiplier here keeps it the same type of graph. It's still exponential decay. It's just going to be stretched out in the vertical direction. So it would be the difference between maybe you've got this graph versus if all these y values get multiplied by the same thing, everything gets higher, but it's still going to be approaching 0. And it's still going to be approaching 0 at the same rate. So we can have this extra multiplier here without changing the shape of the graph, without changing the type of function. It's still exponential decay. And the most important thing about any exponential function, in fact, the most important thing about a lot of functions, but this is especially true for exponential functions, is the derivative. If we differentiate, if we take the derivative, c is just a constant, so we can leave that as it is. But what's the derivative of e to the negative lambda t?
Negative lambda times e to negative lambda t?
Yeah. The exponential function, in general, e to the whatever just stays e to the whatever. But because of the chain rule, we also need to multiply by the derivative of what's inside. In this case, the derivative of that exponent, negative lambda t. And the derivative of negative lambda t is just an extra negative lambda. So e to the whatever stays e to the whatever, but we get an extra times negative lambda because of the chain rule, the multiplying by the derivative of what's inside. And if we rearrange the order of multiplication a little bit, which we can do because multiplication is commutative and associative, negative lambda times c e to the negative lambda t. But what is c e to the negative lambda t? Yeah, that's our original function y. So the result is, the important part of the result here is that the derivative of this function is a constant, specifically negative lambda, times the original function. dy dt equals that constant times the original function y. And it turns out this works in reverse as well. If you start with the assumption that you have some unknown function whose derivative is a negative constant times the function itself, you can rearrange those terms and integrate to get to the fact that y has to be this exponential function. So we can write this as an if-then statement. If the derivative of some function is negative lambda times the function itself, then that function has to be c to the negative lambda t. It's got to be an exponential decay function. And of course, if it was a positive constant, we get a positive exponent, a positive constant in the exponent as well. So this also works for exponential growth. The only difference between growth and decay is that constant positive or negative. Any questions on that so far? And more conceptually, since a derivative just means how fast the function is changing, in this case, how fast it's changing as time passes, what we can say here is if the rate at which something is changing is proportional to how much there is right now, that always leads to exponential change. Could be exponential growth or exponential decay, again, depending on whether this is positive or negative, but they both follow the same pattern in terms of derivatives. And that makes this sort of situation very predictable. Anytime you know that this is true of some function, you can predict that it's got to be an exponential function. And if you know what this multiplier is, you can even write out what this number in the exponent is. What does lambda stand for? The lambda here is a constant that typically represents something about the rate of change. In general, if we're dealing with a situation where the derivative is proportional to how much there is right now, like for instance, if there's 3 times as much of something, then it's changing 3 times as fast. We can always write proportionality as one of the things equals a constant times the other thing. That constant is the value we're calling lambda, or in this case, negative lambda. But it's just a constant multiplier describing how the function's value right now is related to its rate of change right now. And that typically is going to involve other constants, other measurements from the physical system we're working with. Last time we were looking at an example involving fluid flow draining out of a water tank with a leak at the bottom. And the constant ended up being, I think it was density times gravity divided by area times resistance. So that lambda is just some combination of the physical factors involved in the situation we're dealing with. And of course, it's going to vary from situation to situation. The lambda involved in water draining out of a tank is going to be different from the lambda involved in heat flowing from a mug of hot coffee to the surrounding cold air, which is going to be different from the lambda involved in, let's say, air leaking out of a balloon or an electrical circuit charging up a capacitor. So the lambda values will all be figured out in different ways depending on the situation. But the general pattern holds true. If you can write your differential equation in this sort of format, then no matter what constant lambda is, you can write the solution in this format. It's always going to lead to exponential decay if this is true. Any other questions on that so far? So let's try out an example. Actually, let's go ahead and try one of those examples from that webpage I posted on mathandcheese.org/P7B. Let's start with the first one. We've got a water tank that's full up to 8 meters deep. So to begin with, it's 8 meters deep. Let's call that y of 0, because that's the value of y at time 0. And we open a drain at the bottom. Allowing water to spill out. And let's say instead of looking at it in terms of area and resistance and pressure and Bernoulli's equation, let's just say we take some measurements. We take some physical measurements and we find that after 10 minutes of draining, the water is only 5 meters deep. After 10 minutes, water is now 5 meters deep, which we can write in terms of y and t as well. We can write it as y of 10 equals 5. That is when t, the input, is 10 minutes, y, the output, is 5 meters deep. And also after a long time, what would you expect to happen to the tank? If we wait for not just 10 minutes, but if we wait for a very long time. Yeah, presumably it's going to be empty. After a long time, the tank is empty, or almost empty. If you run the mathematics of this, it turns out that it's never truly empty, but eventually it's close enough to empty that it may as well be empty. Because as it drains, you get, you've got a pressure difference pushing water out. As it drains, the pressure difference gets weaker and weaker because you've got less and less water stacked on top. So when the tank is almost empty, you've got almost no pressure difference. So it gets slower and slower and slower. We can write this, though, as a limit. We can say the limit of y as t approaches infinity is 0. It might never get there mathematically, but it's getting closer and closer and closer to 0 as time passes. And these values are really some of the most important things about any exponential decay situation. You want to know what's the value at the beginning or at some instant in time, usually at the beginning. And you want to know what's happening after a long period of time. That alone is enough to sketch out a pretty good graph. If we wanted to graph time versus depth of the water, we know it starts at 8. We know it's approaching 0. And because the depth of the water controls how fast it's draining, like the deeper it is, the more pressure there is and the faster it's going to drain. That means how fast the height is changing is proportional to the height right now. More height means it's draining faster. Less height means it's draining more slowly. That guarantees exponential decay. We know the starting value. We know it's going to approach an asymptote of 0. So we could sketch in an exponential decay curve without even knowing any more information, at least as a rough general idea. Any questions on how that looks so far? If we want to be more precise, though, we might want to know, for instance, like we know, for example, that at 10 minutes, the water is 5 meters deep. We might want to know more information. We might want to know how deep is the water after only 3 minutes, or how deep is the water after an hour, or something like that. Or alternatively, maybe we have a target depth we want to reach. Maybe we want to know how much time does it take to get to only 1 meter deep, or only 1/10 of a meter deep, or something. So to be more precise about this, to be able to figure out what time does it reach certain heights, or how high is it at certain times, we're going to need to actually write out this equation. So let's go ahead and do that. We're assuming that this is y equals something times e to the negative lambda t. In order to really finalize this equation, what variables do we need to figure out the values of? Or I guess I should say, what constants do we need to know?
We would need to know c, right?
Yeah, we're going to need to know c and also
Lambda.
Because ideally, we want a formula where we can just plug in a value of t and immediately calculate y. Of course, we can only do that if we have values for c and lambda. But we can find values for c and lambda by using the data points we have. We know when t is 0, y has to be 8. And we know when t is 10, y has to be 5. And also when t is very, very large, y is going to be close to 0. But that's guaranteed by the fact that this is exponential decay anyway. So let's try using this information. We know when t is 0, y has to be 8. So let's plug that in. We can say when t is 0, y is 8. So if we just copy down this exact same equation, but plug in 0 for t and 8 for y, we get 8 equals c times e to the negative lambda times 0. But lambda times 0 is just 0. What is e to the power of 0 going to be? Yeah, that's just 1. E to the power of 0, anything to the power of 0 is just 1. So that means, what does this tell us? What does this tell us about c? Yeah, c is going to be 8. In other words, c is just the y value at time 0. And we can often use that. In general, if your solution is just y equals c e to the negative lambda t, c is guaranteed to be the initial value. So we often just write this as y equals y naught times e to the negative lambda t, y sub 0. This just representing the starting value at time 0. Now this only works, I want to emphasize this idea that you have times starting value, that only works if it's approaching 0. If it's approaching something other than 0, this gets a little more complicated. But as long as it's just approaching 0, this should work just fine. In fact, you don't necessarily even need to plug in 0, plug in the starting y value. You can just start with the assumption that this multiplier is the starting y value. But the reason for that is because e to the 0 is 1, so you just get c equals the starting y value.
And you said if it approaches something other than 0, it gets complicated. But like I've seen an example where, you know, they put like two fluid systems that are leaking between each other, so the final point is like some set amount. Would that make the problem way super complicated, or?
I wouldn't say really super complicated. It complicates it a little bit by the fact that if you wanted a function that approaches something other than 0, like let's say you want an exponential function that has an asymptote at 5. Maybe it's decaying from something higher towards 5. If you just wrote out something e to the negative lambda t, it would approach 0. So how do you take a function that approaches 0 and move it so that it's approaching 5 instead?
You do plus 5.
Yeah. You could just write it as y equals something e to the negative lambda t plus 5. The complication there is going to be that this multiplier no longer represents the starting y value. This multiplier would instead represent the difference between the starting y value and the asymptote. So for instance, if you started at 8 and you were decaying towards 5, you'd have a plus 5 here, and this y naught wouldn't represent 8, it would represent how high above the asymptote you are to start with. But you can still calculate that. If you forget that idea, you can still calculate it by plugging in 0 for t and the starting y value for y, including the plus whatever to represent the shifted asymptote, and then solve for this unknown constant. So mathematically, it still works the same way. It's just that this constant isn't going to represent the starting y value. It's going to represent the starting difference measured from the asymptote. In fact, it's generally a good idea to think of any exponential decay function as measured from the asymptote. Like if the asymptote is 5 and this value is 8, don't think of this as 8. Think of this as 3 above the asymptote. It's often very useful to just visualize measuring everything from the asymptote rather than from the axis, because the asymptote is really the most important value in the whole system. And this is even true if you've got several functions that are approaching the same asymptote. This function, by the way, this curve, even though it's increasing, it still counts as exponential decay because it's approaching an asymptote. Exponential decay means approaching an asymptote from either direction. Exponential growth means diverging away from an asymptote, regardless of whether it's diverging up towards positive infinity or diverging down towards negative infinity. Those would both count as exponential growth. In this case, though, we would say that this still counts as decay. And what's decaying is not really the value, but again, the difference from the asymptote. We start off far from the asymptote. A little bit later, we're less far from the asymptote, and then less far and less far. So the difference from the asymptote is exactly what's decaying. The difference is getting smaller and smaller. So these would both count as exponential decay, and they both have a plus 5 to incorporate the non-zero asymptote. Other than those differences, it still works exactly like the usual exponential decay function we expect. Any other questions on that? All right, then let's see if we can continue finding the rest of this equation, because we now know that in this situation, we started with 8 meters of depth, so we're going to have c equals 8. So we can fill that in. We still need to find lambda. So what other information could we incorporate here that would help us find the value of lambda? What information haven't we used yet? Yeah, we know that at 10 minutes, after 10 minutes after opening the drain, there's 5 meters worth of water. The depth has decayed to 5 meters. So we can use that information in the same way. We can plug in the value of t and the value of y into the equation we have so far. So let's try that. We know that when t is 10, y must be 5. That's given information. Maybe that's measured experimentally, or maybe it's maybe we have a graph or a data chart, and we can look up when t is 10, y is 5. So we insert that information into the equation. Set y equal to 5. Fill in 10 for t. And also we knew that c is 8. At this point, lambda is the only unknown left, so we can solve this for lambda. And the fact that it's inside the exponent makes this a little bit trickier, but we can still use the core concepts of algebra. What steps do you need to do to isolate lambda here?
Well, you would, yeah, divide by 8.
Yeah, we want to start by dividing by 8. So divide both sides by 8, we get 5/8 equals e to the negative 10 lambda. And now we have this variable locked inside an exponent. How do we get rid of the exponential function?
Take the natural log.
ln, yeah.
We take the logarithm of both sides, specifically natural logarithm or Naperian logarithm, because that's the inverse function of the exponential function. By the way, I wouldn't call it multiplying by natural log, because natural logarithm isn't a quantity we're multiplying by. Natural logarithm is a function, an operation. It's almost like, for instance, if you're taking the square root of a value, you're not multiplying by the square root symbol, you're applying the square root operation. Same idea here. We're applying the logarithm operation to both sides. On the left side, logarithm of 5/8, I'm just going to leave as logarithm of 5/8. We can plug that into a calculator later if we need to, but I'm just going to leave it as logarithm of 5/8. Over here, what happens to logarithm and exponential? Yeah, those are going to cancel out, because logarithm is the inverse, the opposite of the exponential function. So they're undoing each other. We're left with just the negative 10 lambda. And then what's the only thing left to do?
Divide by 10 or negative 10.
Divide by negative 10, so we get lambda equals negative 1/10 times logarithm of 5/8. And since 5/8 is less than 1, the logarithm of 5/8 is going to be a negative number, because logarithm of 1 is 0. So logarithm of something less than 1 is going to give you a result less than 0. So even though we've got this negative here, the overall result is going to be a positive value. One other thing you can do here, by the way, if you've got a logarithm of a fraction, how can you split that up? Yeah, you can subtract. Logarithm of 5/8 is the same as logarithm of 5 minus logarithm of 8. I don't know if that would really be particularly useful in this particular case, but it is often a very useful thing to do. If you've got a logarithm of a fraction, you can always split that up into logarithms being subtracted. Logarithm of the numerator minus logarithm of the denominator. And that also works in reverse. If you've got a logarithm minus a logarithm, you can combine that by just taking the fraction, the ratio of what's inside the logarithms. In this case, though, we may as well just type this into a calculator and get an approximate decimal representation of the number. So negative 1/10 times logarithm of 5/8. And I'm getting about 0.047. So there's our lambda value. We can now fill that in and get the actual equation. Y equals 8 times e to the negative 0.047 t. So this equation describes this exponential decay situation very, very precisely. We can now use this to figure out how much water is left at any time we want. By the way, a quick word on units of measurement. What should the units of t be in this case? Yeah, in this case, t is measured in minutes. Usually we'd use seconds, but any quantity or any unit of time will do. In this case, where the given information is in minutes, so presumably we'll use minutes for t. If t is measured in minutes, what units of measurement does the lambda have to have? Yeah, lambda is measured in inverse minutes. Lambda, if we wanted to write this in terms of units, which we really should, 0.047 inverse minutes. Because the exponent, overall the exponent has to be unitless. You can't raise e to the power of 5 kilograms. You can't raise e to the power of 10 seconds. You can only raise e to the power of unitless quantities. So in order for this to work as an exponent, it has to be unitless. T already has units of minutes, so lambda has to have units of inverse minutes to cancel that out. So this is one of the important properties of lambda in the original differential equation. Whatever measurements, whatever units you're putting together to build lambda in the first place in the physical situation, lambda has to have units of 1 over minutes, or 1 over seconds, or 1 over hours, or 1 over whatever your unit of time is, because it's got to cancel out the units of time in the exponent. What about the 8 here? That's really 8 what? What was that 8 measuring in the first place? Yeah, that was the 8 meters. So it's really 8 meters times e to the negative 0.047 inverse minutes times time. So if you fill in the units of measurement, that's what they would be. In this case, though, we're looking at this from more of a mathematical perspective, and we're just focusing on the numbers. But if you did fill in the units, which usually is a good idea in physics, that's what they would be. 8 meters times e to the negative 0.047 inverse minutes times time. Any other questions on that equation so far? So now with this equation, we can quickly answer questions like how much water will there be after a certain amount of time? Maybe we want to know, like we know after 10 minutes, there's 5 meters of water. What if we wanted to know how much water is left after 15 minutes? What would we have to do? How would you be able to predict how much water is left after 15 minutes total?
Since you already have the equation, you could just plug t as 15.
Exactly. We can just put in 15 for t. So just type into a calculator 8 times e to the negative 0.047 times 15. And that'll immediately tell you how much depth of water is left after 15 minutes. And by plugging in a variety of t values, you can set up let's say a t versus y data table and get lots of data points and make as accurate a graph as you want. Alternatively, if in reverse, let's say you know the depth and you want to figure out how much time it took to reach that depth. Maybe we want to know how much time does it take to have exactly 1 meter of water left. How would you figure out how much time it takes to have 1 meter of water left? Yeah, we can set y equal to 1, and then we need to solve for t. If we want to know how much time does it take to drain to y equals 1 meter, we can set y equal to 1. And then we need to solve for t. So in this case, t is in the exponent. How do we isolate t? Yeah, divide by 8. And then how do you get rid of the exponential function? Right, apply the natural log function. And at this point, it's going to be very similar to the way we solve for lambda. Divide by this constant, take the natural log of both sides to cancel out the exponential function, and then divide by lambda. So t is going to be negative 1 over 0.047 times logarithm of 1/8. And that you can just plug into a calculator, negative 1 over 0.047 times logarithm of 1/8. And we get about 44¼ minutes. So that tells you how much time it takes to decay to 1 meter of depth left. Any questions on that so far? All right, then let's take a look at these two other ideas of half-life and time constant. And we can get those pretty directly now that we have the equation itself. The half-life, how do we define half-life in the first place? What is the half-life?
The time it takes to get to 1/2 of your original value.
Exactly, the amount of time to get to half of the original value. So if we want to find the half-life, from the equation, then all we need to do is set the final amount, y, equal to half of the original amount. Half the original amount would be 4. And then we want to solve for t. And again, we're going to be using the same process we did to find the time previously. Divide by 8. But what's 4 divided by 8? Yeah, 1/2, 1.5. So we can actually start from here. If you want to find the half-life, you don't actually need to know the starting value and take half of it. You can just say, we want to find how much time it takes for the exponential portion to become exactly 1/2. So you can skip the step of plugging in the initial condition and half the initial condition. We can just jump directly to saying we want the exponential function, e to the whatever, to become exactly 1/2, because we want to be able to multiply the initial value by 1/2. So this is another way of thinking of half-life. Half-life is the amount of time it takes for just the e to the whatever part to become exactly 1/2, or 50%. And for the moment, instead of filling in the actual number 0.047, I'm just going to leave this as negative lambda, partly because it's useful to generalize this to see what happens no matter what lambda is, and partly just because it's kind of tedious to write out 0.047 all the time. So I'm going to leave this as lambda. Keep in mind, we're going to solve for t because we know what lambda is. And what would be the next step? How would you continue isolating t here? Yeah, apply the natural logarithm to both sides. So we get logarithm of 1/2 equals, and then logarithm and exponential function cancel each other out. So we just get negative lambda t. And then what else do we still need to do to find time? Yeah, just divide by negative lambda. So t is going to equal negative logarithm of 1/2 divided by lambda. So this is a formula for the half-life. We can now plug in 0.047. Although before we do, another step we can take that's going to simplify this, we've got a negative outside the logarithm. You can think of that negative as a multiplier, negative 1 times logarithm of 1/2. And what can you do with a multiplier outside a logarithm? If you've got a multiplier outside a logarithm, you can bring it into the logarithm and it becomes what?
The reciprocal of 1/2, right?
In this case, yeah, because we got a negative 1. More generally, I would say it becomes an exponent. One of the very important properties of logarithms is that exponents inside the logarithm are interchangeable with multipliers outside the logarithm. If you've got a logarithm with any base, logarithm of, let's say, x to the power of r, that's the same as logarithm of x times r. An exponent inside the logarithm is equivalent to a multiplier outside the logarithm. And while we're at it, let's take a look at the other important rules of logarithms also. We saw earlier that division inside the logarithm is equivalent to subtraction outside the logarithm. Logarithm of a ratio is equivalent to logarithm of the numerator minus logarithm of the denominator. And this is a very useful property. This is really the reason why we define a lot of things as logarithms. Like this is the reason why we define entropy from 7a in terms of a logarithm. Because a ratio inside the logarithm becomes a difference, which you can write as a delta outside the logarithm. So delta entropy is a logarithm minus a logarithm, but you can combine that to get logarithm of the ratio of what's inside the logarithms. So it's often extremely useful to be able to turn a difference into a ratio, especially if you're dealing with numbers that contain some of the same multipliers, because then those multipliers can be canceled out. Also, the number of microstates we were looking at back in 7a often had exponents, often very big exponents, like something to the power of Avogadro's number. Something to an enormous power is very difficult to deal with. But if you can pull that exponent out as a multiplier, multiplying by a large number is much easier than raising something to the power of a large number. So logarithms are tremendously useful in cases dealing with very, very large numbers or very, very small numbers. In fact, this is really what logarithms were invented for in the first place, dealing with complications or calculations using very large and very small numbers. And then one other important property, if you've got multiplication inside the logarithm of x times y, how can that be split up?
Is it log x plus log y?
Exactly. The multiplication inside the logarithm can be split up as addition outside the logarithm. And keep in mind, as you're going through all this exponential and logarithmic stuff, these are completely reversible. If you see logarithm of a fraction, you can replace it with subtraction of logarithms. Or if you see logarithms being subtracted, you can replace it with, you can combine them into logarithm of a ratio. These work in both directions. Either one of these can be replaced with the other. You just want to look at it in terms of what's the context, what or which one of these versions would be easier to deal with. So you're always allowed to make these substitutions. It's not like you see this, you have to replace it with this. It's if you see either one of these, you could replace it with the other if it would be convenient to do so. So think of them as, I guess, more as tools than laws. They're not saying things you have to do. They're saying things you are allowed to do to make the calculations easier to deal with. And one of the most important applications of this one in this particular context is that this multiplier can be brought in as an exponent. So instead of thinking of it as the logarithm multiplied by -1, we can think of it as what's inside the 1/2 raised to the power of -1. And what is 1/2 to the power of -1? Yeah, that's 2, because the -1 exponent just inverts whatever it is. So we end up with, instead of negative logarithm of 1/2, we just get positive logarithm of 2 divided by lambda. And this is typically easier to deal with because we don't have to mess around with a fraction inside the logarithm, and also the negative takes care of itself. So this gives us a very convenient formula for the half-life. In this particular case, we could actually punch this into a calculator because we know lambda is 0.047. So logarithm of 2 divided by 0.047, and we get about 14.74 minutes.
Even if the lambda is negative, are you just dividing it by lambda and not by the negative 0.047?
Yeah, the thing is the lambda is the 0.047.
Okay.
Lambda is not negative 0.047. Lambda is specifically 0.047 here.
Okay, thank you.
Yeah, very good question. We got to be very careful about the negative signs here. If you did use a negative, you just end up with negative 14.74 minutes, which doesn't really make sense in this context, because we should expect it to become half of what it was at some later time, not at some earlier time, because it's decay, not growth. And of course, you can check this by plugging it back into the original function we've got. You plug in 14.74 for t, run the numbers, and you should end up with y equals pretty close to 4, pretty close to half the original amount. It's not going to be exactly 4 because we rounded off some values here, but it should be pretty close. And we can generally use this as a formula for the half-life. In general, the half-life, which is often written as capital T sub 1/2, we usually use lowercase t to represent what time it is right now and capital T to represent a certain interval of time. The half-life is going to be logarithm of 2, because of the 1/2, divided by lambda. So we should always be able to use this formula for half-life. And this also goes both ways. If you know lambda, you can calculate the half-life. Or often more practically, if you know the half-life, you can calculate lambda. Multiply both sides by lambda, divide both sides by the half-life. Because the half-life is often known. Maybe we are watching this water closely and we mark on the clock what time it reaches 4 meters. Maybe we can observationally determine the half-life. And then just take logarithm of 2 divided by the half-life, and we immediately know lambda. Or if you're talking about radioactive decay, for instance, maybe you're dealing with a known element, a known isotope, and you already know what its half-life is going to be. You can use this to calculate lambda, fill that in your exponential decay function, and easily predict how much time it's going to take to decay to a certain other value. Any other questions on that so far? All right, we are out of time for now, but what I'd like you to try next, try running this same sort of analysis on your own, but see if you can use this to find the time constant. The time constant, much in the same way that the half-life was the amount of time it takes to decay to 50% of the original amount, the time constant, usually written as tau, is the amount of time required to decay not to 1/2 of the original amount, but to 1/e of the original amount. That e, 2.718, the same as the e here. And that's, for reference, that's about 37%. Again, nothing particularly special about 37%. It's just that because we're using e as the base of the exponent, 1/e is a very convenient reference point for a certain significant amount that has decayed. So try this yourself. Use the same sort of analysis we did with half-life. Try filling in 1/e of the original amount. Not just 1/e, but 1/e of the original amount. And see if you can figure out what time will lead to that percentage left. And that amount of time is what we call the time constant, just as a useful amount of time for a significant amount to have decayed. Any questions on that? All right, and based on what you now know, see if you can figure out the rest of that problem on mathandcheese.org/P7B. And the next problem also on the same page also involves decaying upwards towards a non-zero asymptote. So see if you can apply the same approach to that as well, and just go through those questions. And feel free to let me know if you have any other questions on that. All right, that's it for today. So I will see you next time.